My name is Caden Taylor, and I am a sophomore physics major at Caltech. Over the summer, I worked under Marius Parapoulou, Mikhail Papucci, and Christian Pina in Caltech's CERN group in using Geant4 to model the propagation of quirks. I will begin by giving everyone an idea of where I will be heading in this talk. I will start with a brief introduction to particle physics and the LHC in order to help contextualize the study of quirks in a broader sense. This will include a discussion of the standard model of particle physics, its issues, and how we hope the LHC can resolve said issues. I will then discuss the theoretical basis of quirks. This includes what they are and how they could fit into the larger picture of solving problems within the standard model. I will then move into why these particles need to be simulated, the main goals of our simulation, and why Geant4 was chosen for simulation work. I will then discuss code design, including how we decided to extend Geant4 functionality to propagate two particles at once. Lastly, I will discuss current progress in actually implementing the code and then wrap up with some concluding remarks. I begin this presentation where any good presentation of particle physics should start, the standard model of particle physics. It is the theory of three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It consists of elementary particles, particles which are composed of no other particles. There are two types of elementary particles: bosons and fermions. Bosons consist of gauge bosons, which carry the fundamental force, and Higgs bosons, which gives particles their mass. Fermions, on the other hand, can be thought of as particles that make up matter. They consist of quarks and leptons and their corresponding antiparticles. Quirks are special in that they are held together by the strong force, meaning they have a property called color, which determines how they are held together. We call this color confinement. Leptons, on the other hand, are colorless and unaffected by the strong force. Altogether, this model is formulated using quantum field theory, which combines classical field theory, quantum mechanics, and special relativity into one powerful theory. However, the standard model as it stands is incomplete. It cannot explain every phenomenon under the four fundamental forces. For one, there is the hierarchy problem, in which the Higgs mass is many orders of magnitude under its expected value. This causes the force of gravity to be much, much weaker than expected, with every other force many orders of magnitude over the force of gravity. Another issue is the issue of unifying forces. The standard model shows that the electromagnetic and weak force combine at higher enough energies to make the electro-weak force. But there is currently not a way for the strong force to combine with them as well. In addition, gravity isn't explained at all in the standard model. And so it's even more difficult to come up with a theory of gravity that unifies with the other three forces. Lastly, dark matter, matter which has gravitational effects but has not been interacted with, is not explained in terms of the standard model at all. Thus, we conclude the model cannot be a complete description of reality. Theorists attempt to solve this problem by bringing forth new models that are extensions of the standard model. Supersymmetry is one of them, but it also includes models such as extra dimensions or the twin Higgs model. Regardless, we realize that the standard model is not complete and we're missing physics. And the question remains, how do we confirm the physics we're missing? How do we confirm standard model extensions? The answer lies in the Large Hadron Collider. Originally created to discover the Higgs boson, it is now used to search for new physics that could extend the standard model. It uses proton-proton collisions to generate new particles, both known and unknown. These particles then decay into particles that are detected by the detectors. This can give signatures of certain particles, which means that if a particle can be noticed, if one knows its signature. These signatures can be figured out through simulation work. Additionally, as the energy of the LHC increases, the possible range of new physics in the LHC can test also increases. Within the LHC, there are 7 experiments that use detectors. In our project, we focused on the compact muon solenoid. But how do quirks fit into this? Quirks appear in one extension of the standard model, known as folded supersymmetry. This means the discovery of quirks would mark important new physics being found that can help complete the standard model. Quirks can be thought of as very similar to quarks. They have electromagnetic charge under the standard model, but they have their own form of color confinement that is separate from that of quarks. We call this scale lambda. This scale has different properties than that of quarks, particularly in the energy of the confinement scale versus the energy of the particle mass. Quirks have the mass scale much greater than the confinement scale, while quarks have a mass scale being much less. Viewing this through the lens of string theory shows how this is relevant. In quark pair production, the two quirks are connected by a string of tension lambda squared. This means that when lambda is much, much less than the mass of the quirk, the energy of the particle outpowers the energy of the string, and the string becomes macroscopic. This is interesting and is not normal. For these macroscopic strings, quirk motion is given by the quirk equation of motion shown at the top, at least when lambda is greater than 100 electron volts, and we can approximate the string as straight. Here, gamma is the Lorentz factor, s is the unit vector in the direction of the string, and v perp and v parallel are the velocity perpendicular and parallel to the string. The force external is the Lorentz forces and matter forces that affect the quirk. If the external force is 0 and the velocities are anti-parallel to each other, there is an analytical solution. However, if the external force is non-zero, the solution must be solved numerically. By examining and plotting the equation numerically, it can be seen that the two particles curve towards one another and depend on each other. This is not how particles usually act under color confinement. Normally, for quarks, the two particles are inseparable. However, quirk motion is weird. That's actually why they're called quirks, due to the quirky detector signatures they yield. Thus, we need to simulate them. The quirk equation of motion can only be solved analytically for very specific cases, specifically when the external force on the quirk is 0 and the two quirks have velocities in the opposite directions. In all other cases, the equation must be solved numerically, already showing the need for some form of basic simulation. What's more is that the interactions with matter inside the detectors cause the external force on the quirk to constantly change, depending on the energy loss due to matter interactions. This makes it impossible to predict analytically when quirks would interact with certain detector elements. If we combine this with the fact that quirk motion is radically different from other particles, we realize we have no clue what a quirk signature would appear like in the detector. We need simulation work to figure out what the signature is so we can do a quirk test. This then brings us to the goals of our simulation task. The first is to have a way to properly model LHC detector elements. This allows us to model areas of the detector that are sensitive to interactions with the quirks and would show up on our detector. We also, secondly, need a way to define properties of the quirk-anti-quirk pairs that would be pair produced in the detector, while also defining the particles that they interact with. These properties include color or charge. These two goals would then be essential for properly measuring and tracking the four-momenta positions and energies of the quirk pair as determined by the quirk equation of motion, along as when and where these quirk hits detector elements. We would need to add corrections to this using matter considerations and use a program that would be consistent with the software used by experimentalists at the CMS experiment. To accomplish these goals, we chose Geant4, an object-oriented framework for particle physics in C++. Geant stands for geometry and tracking, which are two important aspects of our simulation. Geometry in Geant4 is super easy to implement. It is a three-step process in which a detector element is first encoded with just its shape and size, then is given properties such as materials, fields, sensitivity, and is then placed in the overall world. Particles are also implemented simply by first defining a particle by its properties such as mass or color in a particle definition object, and later creating a dynamic particle object. Geant4 is very powerful in its tracking, where it tracks one particle at a time while slowly updating the particle's dynamics one step at a time by integrating over step objects. These steps contain the energy loss information and time of flight information between 2 points and are cut short when a detector boundary is hit, as shown in the figure below. This allows Geant4 to know exactly when certain detector elements were hit and where. Tracking then stops when a particle's kinetic energy drops to 0, a particle oscillates for too long, a particle decays, or a particle exits the world. The steps also determine when different matter processes occur, either before each step, during each step, or after each step, allowing a lot of control over what processes to enact when and where. Thus, Geant4's tracking is perfect for us, except that it can only track one particle at a time. This becomes a problem for us because quirk propagation depends on both quirks. This leads us to design, where most of our time was spent during the summer, as we needed to best figure out how to implement geometry, particles, and tracking. Geometry was relatively simple. There was an example geometry code that could be easily edited to match the geometry of a detector, in this case, the CMS detector. Implementing quirk, anti-quirk particle definitions was slightly more complicated, but still simple. We had to define the properties of quirks and anti-quirks, including mass, charge, color, and PDG number. Then we had to connect these two definitions together by creating a string object that contains information of both quirks, along with creating a way to connect the definition to dynamic particles so they can act like quirks. Lastly, we wanted to be able to read these particles in from a document, as we used example code to do so. As for tracking, quirks are inherently difficult to track in Geant4 due to Geant4 only being able to track one quirk at a time. However, we needed to adapt the code such that it could track 2 quirks at once. This was done by doubling the amount of information within each tracking process, writing new code to do so. Due to the hard-coded nature of Geant4, it was not enough to simply inherit from pre-existing classes. Instead, we would need to create completely new classes for all of Geant4's tracking. This included the equation of motion, steppers, integrators, and chord finder classes. Additionally, we had to choose a single step size for the quirks to follow. They needed to propagate in time together. To do this, we had to compare the step sizes for each step as time steps, and then propagate both quirks using the shorter time step for every single step. This would require constant conversion from length to time and back again. Other issues with tracking in Geant4 include particle deletion, as the quirks must live and die together, otherwise the trajectories will mess up. Both particles should be deleted if one leaves the world volume, for example. On the other hand, the particles should only be deleted if both oscillate endlessly or if both have no kinetic energy, as there may be situations where one is stuck oscillating, but another is free, or one has kinetic energy, but the other propels it. Another problem is the oscillatory nature of quirks. If the quirks are integrated over time steps larger than the period of oscillation, the quirks will be appearing to travel at lower time intervals. This will mess up the equation of motion and desync the quirks. Thus, we must integrate the quirks over time steps lower than the period of oscillation. Lastly, the computational power needed to track 2 particles at once may cause the program to run too slowly. To fix this, we can use the analytical solution given below and approximate the real solution as a perturbative solution of the analytical one. This can only happen if the external force is small, however. Thus, we reach the conclusion that our new code is designed around the concept of pushing Geant4 past its limits by adding new classes that can track both quirk particles at the same time. We now go to implementation. For geometry, we used 5 variables to parameterize the CMS detector geometry: the internal radius, the distance between the cylindrical chambers, the radius of the holes on the lids, the number of chambers, and the thickness. This was simple to implement by just editing the example code, and this ran successfully. As for particle definitions, we made a quirk and anti-quirk definition classes, which had a method definition, which defined the mass charge, the PDG code, and also a quirk string that connects the two and lives and dies with the two. Lastly, the HepMC interface interpreted if a particle on the file was a quirk and assigned quirk definitions and strings to primary particles that would then become dynamic particles if the particle read in was a quirk. This code also ran successfully. Now we move to tracking, in which only partial progress has been made. The quirk equation of motion has been implemented, but it's implemented in a equation of motion class and has methods that exclusively really evaluate the right-hand side of the equation of motion given below. Additionally, we have a stepper over this class that is in charge of actually stepping over the equation of motion. It is a Runge-Kutta method known as the Dorman-Prince method. It's copied from Geant4 code and expressed for 2 quirks. Lastly, we have 4 classes that work together that form integrators for tracking. They are in charge of calculating step sizes for both particles and the changing positions of them. The integrating classes calculate the minimum step size of each quirk over a short amount of time, a time less than the period of oscillation, and then uses the smaller time step to calculate the actual step length and new positions. This is about as far as we got into the code due to the arduous design process. And so this means that it is obvious that more work must be done in order to finish the implementation of quirk propagation. For one, the code for tracking is not yet completed and has only been checked to see that it builds. So we must first finish the basic implementation. So this is finishing coding the tracking. And we must also extensively check the code and test it to make sure that the code is actually running correctly. Then we have to actually validate the implementation. So at the beginning of our summer, we did a simple Python evaluation of the differential equation in a very bare bones way to create hits to see that the new simulation makes sense. So if we compare our results in Geant4, we can then compare it with this Python evaluation and check that our new simulation is correct. Lastly, we will add in extra energy loss procedures in order to model quirk propagation in matter, so the simulation realistically follows that which would occur in the detector if quirks actually exist in the lambda range we chose. This, we conclude that the implementation of the simulation is incomplete, but significant progress has been made. I will now conclude and sum up what I have discussed. So our current model of how the universe and its 4 forces work is incomplete. We are missing some critical new pieces of physics. And one possible new piece of physics is the quirk, a quark-like particle that yields fascinating detector signatures. Simulation of the quirk dynamics in the CMS detector is needed in order to test for quirks in the detector. Geant4 is the tool for this job. Geant4 makes implementing detector geometry and particle definitions easy for quirks. However, it only tracks one particle at a time, leading to the need for creating new classes that allow for the functionality of tracking too. Lastly, the particle and geometry implementations are complete, as is some of the tracking information, but there is still significant work that needs to be done in terms of the project. I would like to end by acknowledging my mentors, co-mentors, graduate students, and people who made this experience possible. I would like to acknowledge Maria Staropoulou, my mentor, and then my co-mentors, Mikhail Papucci and Christian Pina, as along with the graduate student Christina Wang and the Caltech Stern group as a whole, and of course, student faculty programs for offering this experience for me. Thank you.